Hey guys, in this video we are going to take a look at the final problem from the second round of the German Bundeswettbewerb Mathematik 2020. Let's take a look at the problem statement. We have given a table A consisting of m rows and n columns where the entries of the table are non-negative real numbers. Moreover, we assume that the number of rows is strictly smaller than the number of columns of A, and that in each column of A, we can find at least one positive entry. We are asked to prove that we can find a positive element of A such that the sum of elements of its row is strictly larger than the sum of elements of that column. The first thing I want to note is that the problem would be quite easy if we didn't have the constraint that this entry should be positive. Namely, we can take a look at this example table A with 5 columns and 3 rows. And then let us consider these 3 diagonal entries. And we want to compare the sum of the elements of their rows to the sum of elements in the respective columns. Let us assume here, for the sake of contradiction, that for each of these 3 elements, the sum of elements in its row is less than or equal to the sum of elements in its column. After summing these 3 inequalities up over the 3 elements, we get on the left side the sum of all elements in the table because all rows are covered here, and we get that this sum of all elements in the table is less than or equal to just the elements in these columns of the table. This tells us that the remaining columns must have sum less than or equal to 0, which is of course a contradiction because the entries of our table are non-negative and each column must have a positive entry. Note that in order to get this contradiction, we actually needed the fact that m is less than n, which tells us that a positive number of columns remain here. For the real problem, this idea only works if these 3 entries in our table A are indeed positive. As an improvement to this idea, I want to mention that it wouldn't only be possible to take these 3 elements, but rather we can take any 3 or in general m elements lying in distinct columns and rows for this idea to work. We therefore now want to find a configuration of m such points in our table A, and then we would be done. Since we only care about which entries of A are positive for now, I drew a picture of A without any numbers, where I drew a green dot in all of the fields corresponding to a positive entry. In this example, it is clear that we can again find 3 entries in distinct columns and rows that are all positive. For example, let's take these ones right here. But we need to make this approach more general if we hope to solve the problem for all possible tables A. And the key idea for doing this is that we can associate a set of positive entries lying in distinct rows and columns of A with a matching in the following graph. Namely, we take as vertices of our graph the set of rows R plus the set of columns C, and we connect a row with a column, for example 1 with 3, if the corresponding entry, in this case row 1 column 3 in our table, is positive. We say that the set of edges in this graph is a matching if any vertex has at most one incident edge from that set, and moreover such a matching covers R if any vertex in R has exactly one incident edge from that set. Naturally, a matching covering R in this graph corresponds to a set of m positive entries in A that lie in distinct rows and columns. For example, if we take a look at this configuration, then the entry in row 1, column 3 corresponds to this edge, and we can do the same thing for row 2, column 4, and row 3, column 1. And in total, we therefore get a matching covering R in our graph. If you are familiar with matchings in bipartite graph, then now you probably want to apply Hall's theorem, because it gives us a precise characterization for when we can find a matching covering R. Namely, this is the case if and only if, for every subset of vertices x in R, the neighborhood of x is larger than or equal to the size of x. Here, the neighborhood of x is the set of vertices reachable by an edge starting from x. For example, the neighborhood of rows 1 and 2 are columns 2, 3, 4, and 5. This implication from top to bottom in Hall's theorem is clear. If we can find such a matching, then we can just restrict ourselves to those edges and get a neighborhood of x exactly the size of x, and re-adding the remaining edges may just increase n of x. But the interesting part about Hall's theorem is that the other direction also holds, and you can find a proof for that on kalimath.org. If there exists such a matching, then we can use our correspondence to find n positive entries in distinct rows and columns of A, which is enough to finish the proof by our idea from the start. So here we are done, and all that is left is to deal with the other case. Namely, in the other case, we can now assume that we can find a subset x of R such that the size of n of x is strictly smaller than x. What does this imply about our table A? Well, if our first two rows are x, then we want that the neighborhood of x, which we maybe call y, has smaller size than x. So in this example, let's just take the first column as y. And then, by definition of our graph, we know that the rows x only have entries at most in the columns of y. So we could have green dots here, but all of those entries will all definitely be 0. And then we still know that all columns have at least one positive entry, and therefore in the remaining rows, which are in this case just 1, we must have at least one green dot. Since all columns in C minus y have, as I just said, at least one positive entry in the rows R minus x, we know that if we define a table A prime consisting of those rows and columns, it almost satisfies our given constraint. The only thing we need to make sure is that it has less rows than columns. But this follows immediately from our assumption, since C is larger than R and X is larger than Y. Now there's one last tool at our disposal, namely induction. X has positive size, and therefore A prime is a table with strictly fewer rows than A. Therefore, by induction, we may assume that the statement is true for A prime. Here I should note that we don't have to establish a base case any longer. We can always decrease the size from A to A prime until we land in our first case, for which we know that the statement will certainly hold. Now the main claim to finish the proof is that the entry that we find in our table A prime, which I denoted with row R, column C, doesn't only fit the necessary constraints inside table A prime, but also in A. So we should check that row R has larger element sum than column C in the table A. We know by induction that this positive entry has smaller column sum than row sum in A prime. Now its column sum in A is the same than that column sum in A prime, because all of those entries are 0 since those columns are not contained in n of x. We know that those elements here are non-negative at least, and therefore by now looking at A, the row sum may only increase. And therefore this condition here tells us that the same thing must also be true for A itself. The second condition, that the entry in row R column C is positive in A, certainly follows from that condition in A prime, since it is just a subtable. Therefore, our inductive step is finished, so the statement holds in both cases, and we are done.